When considering two or more random variables, their joint behavior is characterized by the joint probability distribution. Now, the joint probability distribution is best summarized in the case of discrete random variables using the joint probability mass function. So the joint probability mass function is going to give us the joint behavior probabilistically for two or more random variables. So the probabilistic behavior of two or more random variables is governed by the joint distribution, and the joint distribution can be expressed via the joint probability mass function. Okay, so what is the joint PMF, or the joint probability mass function? We'll take x and y to be each discrete random variables. The joint probability mass function is going to be the mathematical function that tells us the probability that x is equal to little x, and the probability that y is equal to little y simultaneously. So it gives us the joint probabilities of x and y. When it's clear from context, oftentimes we will drop the subscripts on the function here, right? So we have these subscripts down here. These indicate which random variables we're dealing with. Oftentimes we don't need to include those, and so we might just write this as little p of x and y. Now the joint PMF is characterizing the joint probability distribution. So it characterizes the simultaneous behavior of both x and y. Divides the probability space into all possible pairs of x and y across every one that we might observe. And so if you plug in any pair for x and y, the joint PMF is going to give you the probability that you observe x equaling little x and y equaling little y at the same time. Now, as a result, we can think of this as a type of generalization of the marginal PMF. However, it's accounting for that simultaneous behavior. Right? In the marginal PMF, if you take plug in x equal to little x, right, then you get the probability that that occurs marginally. However, with our joint probability mass function, then plugging in x and y at the same time gives us the probability that we observe both x and y simultaneously. Right? If you have more than two random variables, then we have the analogous definition, right? So if you have x, y, and z, then you could plug in three different values, and it gives you the probability that x is equal to the value you plug in for it, y equaling the value you plug into for it, and z equaling the probability that you plug into it, all at the same time. So as an example here, right, suppose that we have the joint probability mass function of x and y given to us by this expression here, right? So we have that probability is going to be x plus y divided by 21, and this is going to be defined as long as x is a value between 1, 2, and 3, and y is a value between 1 and 2. So what is the probability that x is equal to 1 and y is equal to 2? So the first thing that we note here, right, is that the y equaling, or x equaling 1 and y equaling 2 is going to be given to us by this expression here, and so as a result, we can simply come in and we can plug in to this the values of 1 and 2, right? And this is going to be of the form x plus y over 21, right? Which is 1 plus 2 over 21. And so then you get 3 over 21, which is 1 in 7. So there's a 1 in 7 chance that you have a value of y being 2 and a value of x being 1 at the same time. Okay, and so if we walk through that argument here, right, we want to plug in 1 and 2. That's x plus y over 21. Which gives us 1 in 7 when we simplify down. Now, what is the probability that x is less than 3 and y is equal to 1? Okay, so if we want x being less than 3, okay, then what are the possible values for x? Well, if we go back up, we know that x is going to be a 1, a 2, or a 3. So this is going to tell us that x is going to have to equal 1, or x is going to have to equal 2. Right? In both cases, we want y equals 1 here. Right, so that's y equals 1 and x equals 1, or x equals 2 and y equals 1. Right, so if we want the probability of this, then we can take the individual events and we can sum up their individual probabilities. And that's because these two events right here, right, if we think about these as individual events here, these are disjoint events. You can't have both of them occurring at the same time. And so the probability of their union is the summation of their probabilities here. Okay, and so as a result, we are going to have this be p of 1 and 1 plus p of 2 and 1, right? Then you plug into our expression that we have for our probability mass function up here, okay? And that is going to give us the overarching probability that we're looking for here. And so then clearing this away, we can actually walk through that calculation here, right? So we get 1 and 1 or 2 and 1 as the possible events. Because they're mutually exclusive, then we can add through them, taking the summation there. results in a probability of 5 out of 21. So there's a 5 in 21 chance that x is less than 3 and y is equal to 1. Part C, what is the probability that y is equal to 2? And so if we want the probability that y is equal to 2, right, we can think about this, say, through the law of total probability. Okay, and so this is going to be equal to the summation that x is equal to 1 and y is equal to 2, plus the probability that x is equal to 2 and y is equal to 2, plus the probability that x is equal to 3 and y is equal to 2. Right? This works because those are all of the possible ways that y can be equal to 2. Either y is 2 when x is 1, 2, or 3. And all of these are going to be mutually exclusive events, right? You can't have x being 1 and x being 2 at the same time. And so because these are mutually exclusive and they exhaust the entire sample space, that's going to give us the correct expression there. So then we need P12 plus P22 plus P32, right? We can plug into the joint PMF for each of these, and then we will get the response that we're looking for here. So, walking through that argument, here we're going to either have the events 1, 2, 2, 2, or 3, 2. Right? As a result, to get probability that y is equal to 2, we take the summation of those three probabilities. Doing that results in 12 out of 21, which simplifies down to 4 out of 7. Okay, so now we can ask, well, what's the probability that x is equal to 2 and y is equal to 3? Okay. But here, let's make an important note, right? Y equaling 3, we know that the only possible values that this expression holds for are going to be y is equal to 1 or 2. And as a result, y equals 3 is going to have 0 probability. Right? So here, y has to be from 1 or 2. As a result, we can't observe 2 and a 3, and so there's a 0 probability of that occurring. Okay, so always being mindful of the bounds on your probability mass function. They have to be satisfied for all of the variables at the same time. Let's look at another example here. We take two numbers selected at random from the numbers 1, 2, and 3 with replacement. So you have, say, 3 sheets of paper. You write 1 on one of them, 2 on the other, 3 on the third, and then you put them into a hat. You draw them out, you look at what it is, and then you replace it, and you draw another one. X is going to be the sum of the two numbers, and y is going to be the maximum of the two numbers. And we want to start by writing down the joint PMF of x and y. And so in order for us to do this, we should think about a couple of things. First, if we think about pairs of digits here, right? So we have, say, number 1, which I will use n1 here, and then number 2 using n2, right? How many possible pairs of numbers are there going to be? Well, we have 3 options for the first one. We have 3 options for the second one. And so there's a total of 9 pairs of numbers, right? And these 9 pairs of numbers are all going to be equally likely because we are drawing with replacement. And so each time, each number is equally likely to come up, right? So we could think about writing down all of these numbers here, right? And so we can get the pair being a 1 and a 1. We could get the pair being a 1 and a 2. We could get it being a 1 and a 3. Okay, and then the second one being a 2 and a 2, a 2 and a 1, sorry, a 2 and a 2, and a 2 and a 3. And then you could finally get a 3 and a 1, a 3 and a 2, or a 3 and a 3. And so we have an equally likely probability model with all of these being the possible outcomes that we have here. Now, importantly for us, we need to capture these with respect to x and y, right? So x and y being the summation and the minimum together, or the maximum together, rather. Okay, and so the first thing that I want to do is I just want to go through and let's highlight out the possible maximums. We know that the maximums are either going to be a 1, a 2, or a 3, right? And so in what cases can we have the maximum of a 1, right? In order for us to have a maximum of a 1, we actually have to be just in this case of rolling a 1 and a 1, or drawing a 1 and a 1 rather, right? And that's because if you draw any other value, you're going to have a maximum being larger than 1, right? There's going to be multiple possibilities. And so we can have 1 and 2 going together, and this happens 1 out of 9 cases. Okay. Now, what about if we want the maximum to be 2, right? There's actually going to be 3 ways that the maximum can be 2, right? It sort of makes this L shape or backwards L shape here, right? Either we get a 2 and a 1, a 2 and a 2, or a 1 and a 2. Okay. All other possibilities are going to be larger. And so there's 3 possible values here, right? But what we notice is that if you get a 2 and a 1 or a 1 and a 2, the summation there is going to be a 3 in both cases. So that could be a 3 and a 2. And there are two ways that that can happen out of total of 9, right? Or you get a 2 and a 2, at which point the summation is a 4. The maximum is still a 2 there. And so that happens 1 out of 9 times. Okay. And then finally, the remaining possibilities all have the maximum being 3, right? And so the summations here can either be a 4, and that's going to be if you get a 3 and a 1 or a 1 and a 3. They could be a 5 if you get a 2 and a 3, right? Or a 3 and a 2. Or they could be a 6 if you get a 3 and a 3. And so then we are going to have the possibilities of it being a 4, 5, or 6, right? Each of these with the maximum. In the first two cases, there are 2 possibilities. In the third case, there is just the 1 possibility. Okay, so you have a 1/9 chance of being a 2 and a 1, a 1/9 chance of being a 4 and a 2, or a 1/9 chance of being a 6 and a 3. Otherwise, for 3, 2, 4, 2, for 3, 2, 4, 3, or 5, 3, you have a 2 and a 9 chance. Okay, and so again, working through all of these, we're just using the results from the equally likely probability model, but then we translate this into the language of our random variables over here. And so the PMF is going to be some way of expressing all of these probabilities together. Okay, so let's walk through that again, second time here, just to make sure it's all clear. Okay, so for the possible pairs, we're going to have combinations of x and y being 2, 1, 3, 2, 4, 2, 4, 3, 5, 3, or a 6, 3. Okay, the only way to get an x is 2 and a y is 1 is to get a 1 on each of the rows, and so that happens with 1/9 probability, right? If you want x equaling 3 and y equals a 2, then you need to get a 1 on one and a 2 on the other, right? You can do the similar logic applying, which shows us that there's going to be sort of in order. We have one way of a 2 and a 1. We have two ways of a 3 and a 2. We have one way of a 4 and a 2. We have two ways of a 4 and 3 or a 5, 3. And we have one way of a 6 and a 3. And so then as a result, all of those are going to be out of 9. And so you end up with this probability mass function, which is the same one we were just writing down, expressed differently, right? So there's a 1/9 probability of getting the 2, 1, 4, 2, or 6, 3. There's a 2 in 9 chance of a 3, 2, 4, 3, or a 5, 3. Okay. So this is going to be our probability mass function here. Now we can ask questions about this. So for instance, what is the probability that x is equal to 2y? Right, so x equaling 2y. How can this occur? Well, we can occur here if we get x equaling 2 and y equaling 1. If x equals 3, then we could not do it, right? So if we go then x equaling 4, y would have to be equal to 2. And finally, with 5, you're not going to be able to do it. So 6 and 3 are going to be possible values as well. And so we want to know, in order for x equals to 2y, what is the probability of observing any of the events in this set here? Okay, and so we can add through each of these events, right? If we go back to our PMF, they each have 1/3 probability, and so you're going to have, say, the probability of 2, 1, plus the probability of 4, 2, plus the probability, it should be 1 out of 9 chance, plus the probability of 6 and 3. And so if you add those 3 up together, you're going to get 1 in 3, or 3 out of 9. Okay, so these are the ways that x is equal to 2y, and so then when you add through all of them, you're going to get 1 in 3 chance. Okay, so for x equal to 2y, we have to have the 2, 1, 4, 2, or 6, 3 events, right? If you start summing through the joint PMF here, you're going to end up with 1 out of 3 for those 3 events. Now, what's the probability that x is equal to 2 plus y? Okay, and so if we have y being 1, then we would require x to be 3. If y is going to be a 2, we would require x to be a 5. And if y is going to be a 3, then we would have, in this second case, this would have to be a 4. Okay. And in this final case down here, we would have x being 5 and y being 3. Right. Now, this first situation here is actually an impossible situation, right? Because if y is going to be a 1, that means that the maximum was a 1, and so you could not have the summation being 3, right? So this is going to have 0 probability. The other two are going to be captured using our PMF that we had before. And so a 2 and a 4 is going to have a 1 in 9 chance, and a 3 and 5 is going to have a 2 out of 9 chance. Right? And so in theory, what we would want to do is we'd want to add up the probability of 3, 1 plus probability of 4, 2, plus the probability of 5 and 3, which is going to be 0 plus 1 and 9 plus 2 and 9, which is itself 1 and 3 as well. Okay, and so then we end up with a 1 in 3 chance that x is equal to 2 plus y. So we either are dealing with a 4 and a 2 or a 5 and a 3. Adding those up together, we get a probability of 1 out of 3. So if we now have our joint probability mass function, we can think about how we can get other information out of it. And in particular, we might want to get marginal information out of it. So how does this work? Well, if we think back about the law of total probability, the law of total probability says that the marginal probability of any event A is going to be equal to the summation of joint probabilities here, right? So the sum over joint probabilities of A and BI, where all of the B's together form a partition of our sample space. So if the B's form a partition and then you sum up all of the joint probabilities, then that's going to give you a marginal probability. And so if we think about this, with respect to events of the form y is equal to y, and we partition across events of the form x is equal to x, then what we're getting here is through the application of the law of total probability, we can write the probability that y is equal to any event y is the probability mass function, and that's going to be the sum over all of the possible values for x of the joint probability here, right? And that's because we are going to take the events, say b1 is equal to the event x equals little x1, right? B2 is the event that x is equal to little x2, and so forth. Okay, and so as a result of this, then we have this expression here is a re-expression of our law of total probability, and that can give us the marginal distribution or the marginal probability mass function based on the joint probability mass function. Okay. This process is a process that we refer to as marginalization. So you can take the joint probability mass function and you can marginalize it to get the marginal probability mass function. Ultimately, the rule is that if you sum over the joint PMF and you take one of the variables that you're summing over, it leaves behind the other one. Right? So if you sum over all of your x's, you're going to be leaving behind y, and you get the marginal distribution of y. If you sum over all of your y's, you're going to leave behind the marginal distribution of x, and you get the marginal PMF of x. Okay, so you can write the marginal PMF of x is going to be the sum of the joint PMF over all of the possible values for y. So suppose that we have our joint PMF given to us as x plus y over 21, for x being defined on 1, 2, and 3, and y being defined on 1 and 2. We want first, what is the marginal PMF of x? And so here we can use the marginalization process, right? So we want probability of x, the marginal probability of x, right? This is going to be equal to the sum over all of the possible values for y. And so in our case, that's y equaling 1 up to y equaling 2 of our joint probability mass function here. Right? And so we're going to plug in x, we're going to keep it as y. And so then we can work through, well, what is this summation? Well, when y is 1, rather, we get x plus 1 over 21, right? Plus, when y is 2, we're going to get x plus 2 over 21, right? And that's going to give us our full sums there. So then if we start collecting terms here, we get 2x plus 3 over 21. And this is going to be defined when x is any of the values 1, 2, or 3. Okay, so that's going to be our marginal PMF for x there. Right? So can work through that once again here. So we take the marginal PMF is the sum over all of the possible values for y of our joint PMF, right? If we simplify that down, that gives us 2x plus 3 over 21. And so that's the marginal PMF of x. What about for y? What is the marginal PMF for y? Well, the marginal PMF for y is defined to be the sum over all of our possible values for x, and so that's going to be x going from 1 up to 3, right, because those are the values for x here, and again, of x plus y over 21, right? And so then you're going to have 1 plus y over 21 plus 2 plus y over 21 plus 3 plus y over 21, and so then if we collect those up, you're going to have 6 plus 3y over 21, which is simply 2 plus y over 7. And in this case, we're going to have y being either 1 or 2. Right? And so, again, walking through that process of marginalization here, if you want the marginal distribution of y, the marginal PMF of y, you sum over the joint with respect to x. If we simplify that down, that's going to be y plus 2 over 7, where y is either a 1 or a 2. So the joint probability distribution is expressed mathematically using the joint probability mass function. The joint probability mass function can be marginalized, giving us a marginal PMF using the law of total probability. And as a result, the joint PMF is actually going to capture all of our probability information, not only about the joint behavior of the random variables, but also about the marginal behavior of these random variables. So if you have the joint PMF, you actually have all of the information that you could want to use, whether you're thinking about joint probabilistic behavior or about the corresponding marginal probabilistic behavior.